Good morning and welcome to the 11 o'clock slot on DTrace and Analytics presented by Brian Cantrill. I think you're going to enjoy this slot. Every year there's a presenter that causes the IT staff a little bit of a problem in terms of disappearing for a month or not answering a few emails or not getting to deadlines on time. This year that distinction goes to Brian. But he's a very energetic person, and he's a good for a morning talk. He has once been described as Tigger on speed, so I hope you enjoy the show.
Thank you, Doug, for that introduction. I'm not sure. That feels like my first kindergarten report card, energetic being used strictly as a euphemism for various pathologies. Good morning. I'm Brian Cantrill from Sun Microsystems. I am, I guess, the problem child, at least 2009, for which everyone has my profound and profuse apologies. So this morning I'm going to, and there's actually not a slide up here because this is going to be a very demo-intensive presentation. But if you wondered what presentation you've wandered into, this morning I'm going to give a presentation on visualizing DTrace. And before I get started, because it's kind of implied in the title, if I could, and I'm not doing this for purely self-aggrandizing reasons, but how many of you have heard of DTrace? How many of you know what DTrace is? Okay, that's great. This is the pinnacle of the fame that I will ever achieve, is that a room full of fellow super nerds recognizes the technology that I developed. That's about the end of the line for me. That's great. How many of you actually have used DTrace? That's terrific. How many of you have used DTrace to actually solve a problem? Okay, wow, a smaller number of you. Okay, so just a quick aside, DTrace is a workhorse, not a show horse. So, I mean, it's great that if you've seen DTrace and every once in a while, I love DTrace. Well, have you used it? Well, no, not really, but it just seems great. You should use DTrace to solve your problems. That's what it's designed to do. It's not designed to just kind of be cool or recognizable or what have you. It's designed to actually solve your problems. And indeed, you will find that your disposition towards DTrace changes the first time you actually use it to solve a problem. And those of you who've actually used DTrace to solve a problem can attest to this. And I had this experience myself in developing DTrace. The first time that DTrace saved my ass was it's a fundamental shift that you have from, wow, this technology seems interesting, it's something to play with, to, wow, this technology is something that is really essential to my day job. And if you are a systems administrator and you've got DTrace on some of your systems, be they Mac OS X or Solaris or FreeBSD, really encourage you to actually use them in anger. Use DTrace in anger. That's what it's designed to do. And just to give you a little bit of the history of DTrace, the reason that DTrace is effective for solving problems, or we believe anyway, is because we actually designed DTrace to solve our problems, which seems like a kind of a stupid thing to say. But the reality is there's a lot of software tooling out there, a lot of software infrastructure out there that was not developed by the people who intended to use it. And I think that the best infrastructure, the best tools in particular, are always developed by those who actually need them. And a lot of you have a kind of tools groups or people focusing on tools research or what have you. If they're not actually using the tools they end up developing end up being show horses, not workhorses. And we very much needed DTrace to solve our problem. What was our problem? Well, I came to Sun 13 years ago to work with Jeff Bonwick in the Solaris Performance Group, and the problem that we had was pretty simple. We didn't know why the system sucked. And worse, the sucking is not some persistent phenomenon. The system would start sucking and then stop sucking. Which, on the one hand, it's like, all right, great, the system no longer sucks. But if you're actually trying to understand why the system sucks, that transient nature to the problem is absolutely brutal. And this was hit home for me when I first came to work for Sun, 1996. We were looking at a benchmark rig. This is actually in the winter of 1997. And we had just released a machine called the E10K. Now, I don't want to see a show of hands on the E10K, because let's face it, we all have very mixed feelings about the E10K. There's a lot of love and some pain with the E10K. But E10K was a very exciting machine. It was a 64 processor machine. True SMP machine, and there were a lot of great things about the E10K, really essential to Sun's rise, maybe fall, but certainly rise in the late 90s. So we had just shipped the 64 processor machine, and I was looking at a benchmark run. These guys were doing a huge benchmark run up in Beaverton, Oregon, and they had a serious sucking problem. They're running this benchmark, and the benchmark would run like a champ. And then all of a sudden, it would stumble, and the sucking would start. And it would last like 4 minutes. And the system would be frenetically sucking. And then it would stop. And the system would go back to running like a champ. And they could see, based on the throughput they were getting during the periods in which it was running properly, that we were on track to break the world record for this particular benchmark. But the periods of sucking was the difference between first and worst. They had an unpublishable number with these periods of sucking. They didn't understand what was going on. So they got us involved in Solaris Performance. And at this point, I had never seen an E10K. They're just too expensive. We didn't have one in our lab. And these guys didn't have one E10K for this benchmark. They had 5 of them. These are 5 E10Ks, racked out, 64 processors, 64 gigs of DRAM. It is telling to me that 12 years after the fact, the specs of that machine are still non-trivial. Your laptop does not have 64 processors and 64 gigs of DRAM, not yet anyway. But those machines, you can imagine in 1997, those machines were Goliath. They were huge machines. And it was one machine, one 64 processor E10K to actually run the benchmark, 1 to run the Oracle database, and 3 to drive load onto it. And so we started looking at this machine, and the tooling that we had was incredibly primitive at the time. At the time, actually, the only real tooling we had was a tool that Jeff Bonwick had developed in Solaris 2.6 called Lockstat. And if you use Lockstat, Lockstat was kind of a shard of light into pitch black, really just a shard, though. And we were having to use it to try and understand the system. And it was really difficult because we couldn't really explore hypotheses. We could get some amount of data out of the system, but to actually explore a hypothesis, I had to write a custom kernel module and throw it onto that machine. Now, if you have an E10K or had an E10K back in the day or know of an E10K, or if you've got a big machine today, you know that booting is not a real strength. Those machines took kind of a while to boot. At the time, they took about 90 minutes to boot. So loading a kernel module onto the machine is not really tenable. So what I was doing was I was dynamically loading kernel modules. I was dynamically substituting kernel modules that were being very dirty about the way they were instrumenting the system, and hoping to God that I got it right. Because if I didn't, the system would panic, and I would have like an hour and a half to go figure out why I'm such an idiot. And everyone can kind of twiddle their thumbs while I generate a new kernel module that fixed whatever bug we just run into. And the progress was very, very slow, very frustrating as a result of doing this. So what was the problem? Well, as we were digging deeper and deeper in the problem, it was clear that we were going quadratic in the networking stack. Order of n squared, actually, as I recall, it was like order of n to the 4th in the networking stack. And we found an easy way to reduce that to order of n squared. Great. And we kept digging and digging and digging to understand what the problem was. And as we got deeper, we would discover, for example, we were order of n squared, or order of n to the 4th. But this is a list that should never have more than like 4 things on it. So why did it have 1,000 things on it? OK, well, yet more custom kernel modules. Dig, 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 dig. And all along, we're getting deeper and deeper and deeper and deeper. And my assumption the entire time is that when we get to the final answer here, it's going to be deep in the bowels of the networking stack. There's going to be something imperfect, suboptimal about the implementation. We're going to switch that, and that's going to be the problem. And boy, was I wrong. Because when we got to the end, when we finally figured out what the problem was, what was the problem? The problem was that the machine had been misconfigured. It had been misconfigured to act as a router. Etsy no default router was not set. And they were seeing sporadic router failure elsewhere in the lab. Router would pop, and the world's slowest, most expensive router would volunteer to start routing packets. So the benchmark machine would furiously start routing packets